Hello, everybody, and welcome.
Hello, everybody, and welcome.
Hello, everybody, and welcome.
Hello, everybody.
At least it happens really fast, so I can edit that out later. Okay. Hello, space fans, and welcome to this Astro Coffee Hangout. My name is Tony Darnell from deepastronomy.space, and I know you're excited about today's hangout because we are going to be talking about exomoons. That's right. It's not exciting enough for deep astronomy space fans to talk about planets around other stars. Oh no, we need more. You guys want exomoons, and you ask about it every single time. Every hangout we have on exoplanets or life in the universe gets quickly dominated with questions like, well, what about exomoons? Can we see any exomoons yet? Well, today is your day, Exomoon fans, because my guest today has been using the Hubble and Kepler Space Telescope data to look at one of the exoplanet candidates from the Kepler mission, an exoplanet around the star known as Kepler-1625. It's a star located some 8,000 light years away, and not surprisingly, in the constellation Cygnus the Swan, because that's where Kepler stared for 5 years. Well, Kepler-1625 has a huge gas giant, which is called Kepler-1625b, in orbit around it. And maybe, just maybe, going around that might be an exomoon. It might be a moon, but we call them exomoons, if we would. Okay, so today we're going to be talking with the first author of the paper that appeared in the journal Science Advances and describes these observations in detail. And I put a link to that paper in the description box on YouTube, and so you can follow along. It's also on deepastronomy.space/live. And before I start, though, I need to take care of a little bit of business. I need to let you guys know that these hangouts are sponsored and endorsed by the American Astronomical and the American Astronautical Societies, and they are designed to bring the latest discoveries and advances in astronomy directly to you by inviting the astronomers who are doing the work. And we bring them here to these hangouts. And we hope you will ask our guest questions live, but I know many of you are probably watching the VOD of this, or maybe you're listening to the podcast version of this broadcast, so which is after the fact. But I still want to welcome you, and I would invite you to leave comments in the description box below anyway, and I'll try to get to them. If I can't, maybe I can forward them on to my guest, and he might be able to take some time to answer. Let me just check the streams real quick. Okay, yep. So far, no big disasters. Everybody is listening and responding. So apparently I'm being heard, which is always a good sign. Okay, so let's go ahead and get started. Oh, I should mention that Carol Christian, my co-host, is on travel today and was not able to join us. Nothing to do with the hurricane, at least as far as I know. She does drive back and forth between Baltimore and Florida quite a bit. And I'm here in Central Florida, and the sun is shining, and we never had any power outages. It missed us, so we're all safe and sound here in Central Florida. So that's always a relief. We dealt with ours last year, and the year before that. So I guess it's the Panhandle's turn. I don't know. But anyway, let me bring up my guest today. His name is is Alex Teachey. He is an NSF research fellow at Columbia University. He's also the first author of the paper we're going to be talking about. Welcome, Alex, to our humble little hangout. It's good to see you.
Thank you very much for having me.
The weather looks great where you are.
It's been lovely the last couple of days.
Yeah.
Thankfully.
Well, hopefully you're not going to get a lot of yuckiness from Michael as it heads its way northeast, but
hopefully not.
I think it's gonna even affect DC at some point, but I'm not totally.
Oh, is it really? Huh.
I'm not totally sure. Okay, so let's start like we always do with a summary of your research. You've been using Kepler and Hubble data. So why don't, without giving away all of the stuff, I've got lots of plots here and things like that we're going to go through in detail. Why don't you give us an overview of the research question you were trying to ask, and then we'll talk about maybe the details of the star system itself and the planet and the moon.
Sure. Yeah. Okay. So we originally were performing an analysis of many different planets, of almost 300 planets in the Kepler data. And in the course of doing that work, we identified this single candidate, Kepler-1625b, which looked had to, what we expect a moon to look like with a planet. We're looking at transits of the planet. So this is what happens when a planet passes in front of a star from our point of view. The planet blocks out a little bit of the starlight. And so if you're monitoring the brightness of the star over time, you'll see a little dip in the intensity of the starlight. And if there's a moon orbiting that planet, then we'll see a big dip due to the transit of the planet, and we'll see a smaller dip due to the transit of the moon. So this was the signal that we thought we saw in the Kepler data. It looked pretty convincing and tantalizing, but not quite enough to claim a discovery. So what we really felt was that we needed a follow-up observation with Hubble. And so we asked for that time, and we were awarded it about 26 orbits on Hubble, which amounts to about 40 hours time on target. We monitor the brightness of the star again when the planet transited in October 2017, and that's so that was the crux of this latest effort.
Great. Now because you started with Kepler data. Is Kepler-1625b, is it a candidate or is it confirmed? And let's explain the difference real quick.
Right. So it's considered a confirmed planet. The initial science team went through and identified candidate signals, and eventually they had these things called threshold crossing events. They're just looking for signals that might be a candidate, and then sort of the next stage there is to be called a KOI. This is a Kepler object of interest. And then eventually, through some validation work, the planet becomes a full-on, confirmed planet, and then it gets a Kepler name, Kepler-1625b in this case.
Okay, so yeah, and because it uses Kepler. Now, this is also from Kepler data, not K2 data, right?
That's right. This is the original Kepler mission.
Yes, because so just so you guys know, they did some amazing things with Kepler, which, by the way, I think is on its last leg at this point, where they have recommissioned it as K2, where it looks at areas other than the constellation Cygnus. But its primary mission was to stare at Cygnus for 5 years, which it did, and get all of these light curves. Okay, what about 1625b? What is it? What kind of planet is it? Give us some bits about what you know about its size and its orbit.
Right. So the planet is about the size of Jupiter. As far as we can tell, it's a little more massive. Our best estimate places it somewhere around 3 Jupiter masses, but that's not terribly well constrained. But a little more massive than Jupiter, but about the same size as Jupiter. And this is what happens if you're looking at the mass-radius relationship of objects around this mass radius regime. As you start putting on more mass, the planet actually starts shrinking a little bit. It's sort of getting crushed by its own weight. So it's about the same size as Jupiter, but a little more massive. The moon, as far as our modeling suggests, is about the size of Neptune. And that's something that people really haven't anticipated much in the literature. We think about the solar system moons. They're all, significantly smaller than the Earth. So to see a moon of this size was sort of unexpected. The star, based on our modeling, is as you pointed out, about 8,000 light years away. It's about the same mass as the sun, but larger than the sun. We think it's climbing the giant branch. So we know the red giants exist. Think about Betelgeuse in the constellation of Orion. This is an enormous star. I think the size of Betelgeuse is about the size of our inner solar system. So not nearly as large as that, but because we think the star is in a late stage of its evolution, it is on its way to becoming a red giant.
Okay, and so while you were talking, I was showing that that animation of the moon going behind the gas giant that NASA had created to give sort of an idea of the scale of these things. So a Neptune-sized exomoon. How unusual do you think this is?
Well, that's very difficult to say right now. This is potentially the first moon that we've ever discovered. So so we don't have any population statistics yet about these things. What I can say is that, theoretical modeling doesn't rule these things out. There's some people who have done modeling that says, okay, well, in 1% or 0.5% of our models, you produce a moon this large. So we analyzed in our earlier work about 300 planets. We identified this one object that looked like it might be a moon. So that's about the right numbers, right? Something, so, less than 1% of the cases, you're going to see something like this. And even though it's been unanticipated, you could make the argument that because it is the largest, because it is so large, this is in some ways the lowest hanging fruit, right? We ought to see the biggest ones first, just like we saw the biggest asteroids before we saw all the smaller ones.
That's a really good point, because these dips in brightness, the bigger they are, the easier they are to see. So
exactly right.
You're right. That is low hanging fruit. But I want to go back to your statement about the mass. You said that it was about the size of Jupiter, but more massive. I thought the transit method didn't tell us anything about mass. I thought it told us about size and the period of the orbit. And did you say what the period was? I didn't.
Yeah, that's correct. We don't get a direct mass estimate from the depth of the transit. We are chiefly measuring its size.
Right.
We do derive a mass ratio when we model the planet and the moon system. You can deduce the ratio of the masses of these two objects, but then in directly inferring we have to infer the mass. And so
right.
As I was mentioning, we have a pretty clean understanding of this mass radius relationship. So if you you give it a radius and you can get some probabilistic estimate of what the mass of the planet is, you can do the exact same thing with the moon. So the radius of the moon, again, from the transit, and so you can get some probabilistic estimate of the moon mass. And so putting all of these numbers together, we can make some inferences to the masses of these objects, but it's not terribly well constrained because we don't measure it directly.
Okay, so because there are models out there, you've seen a lot of planets with certain sizes. We have also made radial velocity measurements, which do give you mass of an object. Then from that, you can construct a relation, like you say, a mass radius relationship that seems to hold up.
Exactly right. Okay. Yeah, it's fairly well constrained. There is a small subset of the planets that we know now that we have both size and mass measurements, and so we can sort of look at this empirical relationship and make some estimates about the mass based on the size.
Okay, all right. Well, there's something else I just learned, and every time we talk about exoplanets now, I'm going to ask about this until I understand it right. But I learned a couple of hangouts ago where we were talking about habitable zones in a couple of weeks ago hangout where I learned that the size of a rocky exoplanet, the radius of it, can tell us. There's also a relationship about whether it might have an atmosphere or not. Now, this is based on solar system formation and evolution. But they say, and do you know anything about this? You may not, and that's fine. You don't. But based on the size of a rocky planet, I guess it has to be a rocky planet. You can infer whether it has an atmosphere or not. Like super Earths are generally thought to have an atmosphere.
Right. So we can, make some inferences. This is a little outside of my area of expertise, but we can make some inferences about their composition. When we have a size and also a mass measurement, we've seen papers coming out and saying, oh, well, this is a water world. We can tell because of this, this density of this world. With regard to the atmospheres, this is sort of cutting edge science now. We are trying to, when a planet transits, passes in front of the star, the light, just a little bit of the light is passing through the atmosphere of these worlds. And it turns out that if you have, atoms or molecules, usually in this atmosphere, these molecules will absorb some of that light at a very specific wavelength. So we absorb more light at some wavelengths than others, and so that effectively makes the planet look larger or smaller at different wavelengths. And this is a way that people are trying to measure the composition of these atmospheres, and sometimes you can even maybe infer the mass of these objects based on what we're seeing in the atmosphere.
Okay,
but
good.
that's really cutting edge, and that's kind of where a big part of the field is going.
Yeah, and the context of that question was we were having a hangout on on Vulcan, the planet, Epsilon was it 40b? I don't have the in front of me right now, but it was Eridani, sorry. And they were already talking in the paper about an atmosphere, and I called them to task on that and said, how can you possibly know if there's an atmosphere there if all you have are transit data? So this was from tests, and so I just, I thought I would ask about that because it's something
right.
That
So
I'm still...
in the case of the Kepler observations are pretty much just white light. They're taking in light at a broad range of wavelengths. The Hubble data, by contrast, we actually do have wavelength information about this target from about 1.1 to 1.7 microns. And so that's near infrared. And so we could look at the depths of these transits at different wavelengths and try to say something about the atmosphere. Turns out that this star is so faint that our error bars are really large, and we couldn't really make very firm inferences about this atmosphere. But it is possible, particularly with Hubble data.
Okay, I want to get to your data and I want to show the light curves, but let me get to a couple of questions real quick because they're pertinent to what we're talking about. Peter Quinn is going, is this possible this is a captured planet, this Neptune-sized exomoon? Could it have gotten there by being captured? Because it's hard to imagine, isn't it? How
right.
It could have
formed. That's an excellent question. It brings to mind, for example, Neptune's largest moon, Triton, is, as far as we know, a captured object from the Kuiper Belt. This is obviously much larger than that, and so it really makes you wonder where something like this might come from. This was really the first question that any astronomer worth their salt was asking when they saw this thing. How do you get something like this? There's basically three mechanisms to form a moon, right? We think about the impact scenario, the way that most people think that we got our moon. There's this capture scenario, and then there's a disk of material around the planet out of which these moons coalesce. So before I was talking about theoretical modeling potentially being able to explain something like this. A capture scenario is also, somewhat feasible. I'm not a dynamicist, so I tend to be, as an observer, I tend to let the data speak for itself. There's any number of phenomena that we have observed in the universe so far that the theorists are still debating how you can get something like this. I think about hot Jupiters. These are planets that are about the size of Jupiter, but orbiting extremely close to their star. Some 20 years after their first discovery, the theorists are still trying to figure out how you make something like this. So what we've learned is that nature is sometimes very good at making things that we haven't yet figured out. A capture scenario seems like it could be the case. You might think that this is strengthened a bit, considering the fact that as our modeling suggests, the inclination of this moon with respect to the plane of the planet's orbit is quite tilted. It's about 45 degrees tilted with respect to the planet's plane. And that's, again, not terribly well constrained by our modeling, but that's what it suggests. So that immediately calls to mind, this looks like something a little unusual happened in this case. But again, because we don't have population statistics right now, it's hard to say how unusual that might be.
Okay. And Larry Keese has a question on the naming convention for this. So we have Kepler data. We know that there are Kepler KOI objects of interest. The stars are given a designation, like in this case, 1625. And then the first exoplanet is usually denoted with a little b, right?
Right.
And so why little b, by the way? Why not little a?
I don't know the answer to that question.
Yeah, nobody seems to.
Yeah, okay. I don't. I'm sure there's a good reason behind the star. I guess is A, but or maybe they're leaving room. But now once they start discovering planets, sometimes they just discover them interior or exterior, and then the letters get all kind of.
I know, because if it's a double star system, there could be a Kepler 1625 capital A and a capital B,
exactly.
But the planets are little b, and then on down the road. Same with like TRAPPIST, the TRAPPIST-1 system. Exactly. Okay, what about exomoons? Is there a naming convention for adding an exomoon to this? Hopefully it's not going to be another letter.
Right. So this is something that the International Astronomical Unit, the IAU for short, they'll eventually have to come down on this. I think when we start discovering more of these things, the IAU will take a stand. My personal preference is to use Roman numerals. This is a naming convention that has been used in the solar system for hundreds of years. You think about the 4 big moons of Jupiter, the so-called Galilean moons. These are Jupiter 1, 2, 3, and 4. With Roman numerals. So that is, I kind of like that. It's nice and clean. And, so that's what we've advocated for. We called this Kepler-1625b1. Then later on, we said, well, this is not a confirmed discovery at this point. We're considering this a candidate still. And so we took to using a lowercase Roman numeral.
Yeah, 1. I can see a real can of worms here. You've got an object of interest and you've got a candidate, but then it's a confirmed. What if the planet is confirmed, but the moon isn't? Then you've got a moon or planet.
Exactly right. Yeah, so that's why we started using this lowercase Roman numeral. But there's other opinions out there. We've been contacted by folks who have opinions about what this thing ought to be called. So eventually the IAU will have to.
You know what that reminds me of? It reminds me of the way we categorize stars, like population 1, population 2, and 3. But there's no rhyme or reason to what these stars are. That's what it reminds me of. Okay, so let's get to your observations and data. Now, while we're talking about this, I'm going to go ahead and show that little animation of the data points and all of that kind of stuff. Just, you said you got how many orbits of Hubble data, of Hubble time?
26 orbits of Hubble. These are orbits of course, the telescope orbiting the Earth. That's how they sort of hand out.
Did that include all of the stars that you had in your survey, or was it just this star?
Just this single target.
So you looked at this star, 1625, for those orbits.
40 hours.
Oh, yeah, 40 hours.
Orbits, about 40 hours, yeah. That's exactly right.
Okay, and you built up this light curve. Now I'm going to animate through the light curve while you're talking about it. It'll just loop.
Right.
So maybe go ahead and describe what we're
sure.
looking at.
Yeah. So, because we're monitoring the brightness over time, this is why we have to spend so much time looking at this object. And the planet is got an orbital period of about 287 days, right? So it takes a long time to make one orbit of the star. And you can imagine that the longer it takes to complete these orbits, the slower the transit occurs. So the transit of the planet by itself takes about 19 hours. And so when we're looking for a moon, we're really looking on the wings of this planetary transit. The moon could, come in first, it will come in after the planet. And so we've got to monitor the star for a fair amount of time around that 19-hour planetary transit. So this is why we need so much time, and this is pretty unusual to devote this much time to not only a single target, but also to a single transit. Several other observations of other transiting planets have been performed with Hubble, but they usually monitor multiple transits, and they're usually these hot Jupiters, so they come around every single day, and the timing is not quite so critical. So we had 26 orbits with Hubble, and what you can see, Hubble is going around the Earth. So you'll see in the data, you'll see these little gaps. Hubble can stare at the target for about 50 minutes or so at a time, and then it goes around the Earth, and so it's blacked out for 45 minutes. So this is what the data looks like. We see that central planetary transit, and then we see what we are attributing to the moon, this secondary dip in the data following the central planetary transit. One other thing that I will say, it's not just this dip that is our case for the moon. Another key part of this analysis is that when a moon is orbiting the planet is, of course, pulling on the moon, but the moon is also pulling on the planet. And so because of that, the planet sort of wobbles around a little bit as it goes around the star. This causes what are called transit timing variations, meaning sometimes the planet transits early, other times the planet transits late. In this case, the planet transited about 78 minutes earlier than we anticipated. So we think there's pretty clear evidence that there are transit timing variations in this system.
Now, that was the pull of the moon on the planet causing that variation.
Right. Mm-hmm. Yes, that's right. So we are attributing this transit timing variation as well as this dip that we see after the planetary transit these sort of two lines of evidence are the key parts of the case for the moon.
Can you glean from this what the moon is doing around the planet? Do you know anything about its orbital period? You said it was 45 degrees inclined, right, with respect to the planet or the ecliptic plane of the system?
The ecliptic plane of the system. So the plane of the planet's transit. So you can see in this animation, if it's still running,
it is, yeah,
how tipped up it appears. So yeah, we derive an inclination for the moon. We derive the what's called the semi-major axis, the orbital separation of the moon and the planet, and we have a mass ratio, as I said before, between the moon and the planet. That gives us the orbital period of the moon, which is somewhere around 20 days or so.
Oh, really? There's a lot about this. It's like the Earth, 287-day orbit. That's not too different from our 365-day orbit. And would you say 20 days?
Something like 20 days, yeah. So again, these are not terribly well constrained by the data that we have in hand, but that's what the modeling suggests, yeah.
Okay, all right. And okay, so that is how we know this is your evidence, and this coupled with the transit timing variations suggests that this thing is wobbling with respect to a moon that could be there. Is there anything else it could be?
Sure, yeah. So it's certainly plausible. Transit timing variations have been seen many times. As I said before, this is potentially the first exomoon, but we definitely see transit timing variations in other systems. Those are typically due to another planet in the system. So that's certainly a plausible explanation. Now,
I was going to go there. Could there be a Kepler-1625c maybe out there?
Right. So that's certainly plausible. The key point is that we haven't observed one of these planets. That doesn't mean it's not there, of course. If there were a planet external to Kepler-1625b, the geometrical transit probability of this planet really falls off very rapidly. You can imagine the farther a planet gets from the star, your angle of viewing has to be just right. We can see a wide variety of angles when the planet is close to the star, but the farther away you get, we have to be really perfectly edge on to see it. And so it's certainly plausible that something could be there, but we haven't detected it. At the same time, we think we're pretty sure that we haven't seen any other transits of an interior planet. We really should have been able to see that in the Kepler data, and we don't. Again, there could be something out of the plane that just is not transiting.
Is that because the plane of the inner planets are probably going to be pretty close to each other? So if you've got one, you're probably going to get others if they're there. But if you're way far out, that if it's slightly like Jupiter doesn't orbit around on the exact same plane as the Earth does here. It's a little bit different. So if it's way out and maybe a little bit different, you wouldn't see the outer ones. I get that part, but if there were other inner ones close to this,
right. So the expectation, based on the solar system and based on what we've seen in other systems now, is that they are more or less coplanar, meaning on the same plane, but not right on necessarily. When you have interior planets, though, we've got more room to work with. As I said before, the closer the planet is to the star, sort of the more wiggle room you have in terms of these relative inclinations. Again, there certainly could be something in the system that's just not transiting interior or exterior. But now you're going after another hypothesis that hasn't been demonstrated. Certainly plausible. Maybe Occam's razor, it could be another planet in the system that we haven't seen. But that doesn't explain this dip that we see in the light curve. So the moon hypothesis has the sort of benefit, even though it's an extraordinary claim, and we fully recognize that.
Sure.
It has the benefit of being a single explanation for these two phenomena.
Okay, so be honest, Alex. You saw this light curve, and what was your first thought when you saw this thing? Were you like, huh? What is that? Or must be another planet? Or what was your first thought?
Well, we got very excited when we saw the Kepler data, the original Kepler data. When we saw those signals, we thought we were getting fairly excited, and this was really the first time my advisor David Kipping has really been a pioneer in the Exomoon search, and he's been working on this stuff for basically a decade. This was the first time that we had ever proposed for Hubble time, so this was the most promising candidate that he had ever seen. And I,
and even to just get Hubble time to do this had to be a strong science case. So that was really a compelling part of your favor too, because the time allocation committee.
Exactly right. Now, when we saw the Hubble data, we have learned, both of us, that you really can't eyeball these things all the time. There's natural bumps and wiggles in the data that might be due to the star, it could be due to the instrument, and so you really, really have to put the data through its paces. Make sure that what you're seeing is not instrumental and not some other astrophysical effect. Right. So that's a very painstaking process. But
it's a familiar one with Kepler data by now, isn't it? I mean, sure. People have gone through this pretty well.
Sure, but this observation with Hubble in particular is pretty unprecedented. To look at such a cold planet so far away from its star, to look at it for so long. And it's a very faint star, much fainter than ordinary Hubble targets for transits. And so all of these things made, kind of put us in uncharted territory. So we had to, really take our time with this thing. And to be perfectly honest, I was always kind of expecting, once the evidence started coming in that maybe this really is a real thing, I kept expecting some test would come along that would make this thing go up in smoke. We didn't come up with any ultimately we tried to throw everything at it that we could think of, and the moon hypothesis kept surviving. So eventually you start to get more and more comfortable with the idea that maybe it really is a real thing. But at least for myself, I didn't ever get really excited, because we've all seen these sorts of things evaporate in the past. So you gotta temper your expectations a little bit.
Exactly. But my understanding is the way a lot of the Kepler candidates got confirmed into exoplanets was done largely on the ground with ground-based telescopes. First of all, can ground-based telescopes help you here? Can you go to, say, HARPS or on ESO or some other maybe a radial velocity telescope or something to help you with this confirmation? Or what do you need? Sure. What kind of observations would you ideally like now?
Right. So radial velocity measurements would be great. We really would like to get a firm measurement of the planet, for example. That would, as I mentioned before, we've got a mass estimate for the planet, but it's not terribly well constrained. So if we got to radial velocity measurements, that would really nail things down great. At the same time, that might also reveal potentially another planet in the system. And so that would be an important sort of cross-check that we are really not seeing, that these transit timing variations are not due to another planet. Those would reveal both of those cases. In terms of looking at additional transits, however, because this event is so long, as I said before, it was a 40-hour observation on Hubble. Earth is turning. So, you never get a 40-hour night unless you go, in this case, really far to the north. We did the calculation. You have to be north of 78 degrees northern latitude. So there's no telescopes up there. And so you can't perform this observation with any single telescope on the ground, which would mean that you would have to propose for time on multiple telescopes, hope that it's not cloudy on the critical time of the transit, and then you'd have to stitch together multiple heterogeneous data sets in order to perform an observation like the one that we did. So you really have to go to space for this, and there's really only a couple of telescopes. Spitzer could potentially do it, but really Hubble was the best game in town right now.
So I'm trying to visualize what you're saying. So because you need 40 hours to get this transit, and the Earth spins once every 24, right. You can't, if you happen to start your observations luckily at dusk, and it was just hitting the limb of the star, you're only going to get however long the night is, and that location.
Maybe right. Yeah, the farther north you go, say if it happened in the summer, for example.
Yeah,
you could go in the northern hemisphere. And you could go farther north and get more hours of. Excuse me. You'd want to perform this in the winter time, so you'd have maximal nighttime.
Got it.
So the farther north you go, you'd have longer and longer nights. But we did the calculation a long time ago, and you have to go north of 78 degrees in order to get up there, and that is comfortably
ain't nothing up there.
Ice sheets, just the Arctic Ocean. So no way to perform an observation like this with any single telescope.
Well, you know what this does now, right? You're an early career scientist, right? This means you can propose and get funding for a what you can call a high latitude observatory. That's what you should call it. And
Antarctica might be another story, but I'm afraid we're running out of ice up there. I don't know. A boat wouldn't do too well.
Yeah, maybe sort of a Sophia type thing that can stay up. Oh, hey, what about something like Sophia, where you could fly? You could fly. You could counteract the Earth's rotation.
Now, the Sophia, does it have refueling potential in the air?
I don't know. But
now we're talking about sort of like
okay, all right.
B-29, constantly in the air kind of things.
Okay, so fine.
It's a long observation.
So what you're telling me now, though, what I'm getting from all this is that it's going to be hard to get confirmation of this.
We've asked for more time on Hubble, and we'll have to see. We should be hearing not too long from now whether or not we get additional Hubble time.
Hubble's a little scary right now.
We were talking about this though, and we kind of thought that whether people think this is real or people are very skeptical that this is real, both of these camps would really want to see an additional observation of the system in order to nail it down one way or the other. So hopefully we've made a decent enough case that we really ought to be observing this thing one more time. The nice thing about this next transit coming up in May 2019 is that we have a pretty clear prediction for what we expect this transit to look like. Okay. When we had the October 2017 transit, we didn't have a very clean prediction at all as to where exactly the moon should be showing up. This time it's much cleaner. And so if we could make this observation and it appeared more or less like we were expecting it to, then I think that would be a pretty solid case that it's really there, but we have to see.
Okay. One more question. I'm going to get to the live chat here because there's a lot of good stuff building up. I take it from the sound of it, that when the transits are going to be. We know how long they are. It doesn't sound like TESS, the Transiting Exoplanet Survey Satellite, is going to be helping you much here, is it?
I don't know terribly much about the capabilities of TESS, to be perfectly honest. We've tend to think about it in terms of the Exomoon search more generally, using the TESS data much the way that we use the Kepler data. The big difference with TESS is that it has a much shorter baseline for any particular part of the sky, right? It spends about 27 days or so looking at one part of the sky, and then it moves on. Now, there is a zone around the northern equator, the pole, the ecliptic pole, where is called the continuous viewing zone, and they'll have data for about a solid year in that region of the sky. But we're tending to think now that the moons are going to be fairly far away from their host stars. The planets are going to be colder, much more like a Jupiter or Saturn or something like this. Colder planets, these look like they're going to be the best candidates for finding the moons. But those come around very, very rarely, and so TESS unfortunately won't see them. We may be able to get lucky and see a transit of this planet, if TESS just happens to be looking in the right place at the right time. I'm actually not sure yet whether or not this will coexist.
So if it is going to help, it's going to have to be in that continuous observing zone, like you pointed out.
I'm pretty certain that this target is not in the continuous viewing zone. So TESS would really just have to, by chance, be pointing in the right place at the right time.
Yeah, that's a real shame because it has to be in the sector at the time, and then it has to be doing some kind of transit during, the planet needs to be transiting while it's looking, and boy, that's just not.
And as far as I know, the TESS will continue. The next transit's in May 2019. I think TESS will still be looking at the southern sky at that point, and this object is in the constellation Cygnus. It's definitely in the northern sky, so we probably won't catch it this time around. But I haven't run those numbers.
Well, there is hope though for TESS, because after it finishes its 2-year survey, they're not just gonna turn it off and throw it away. It's still going to be up there doing its thing. I think they're going to be redoing some of the science definite requirements for it after it finishes the initial survey. So there's still a chance TESS could maybe bring some light to bear on. I like.
Hope so.
That was good.
Whatever
light to bear on this. Yeah. Okay. Okay. So let me. So on Facebook, Jeffrey Scott wants to know. other than the transit and the wobble methods, that's the radial velocity. That's where you, by the way, we didn't define that. That's where you measure a spectrum of a star and you look at its wobble of the spectral lines as the planets pull on that star. And that's how you can get how much mass that star has, because how much it pulls, how much it wobbles is an indicator of its of the planet's mass, or whatever it is that's pulling on it. So other than that, other than transit and wobble, are there other techniques that we have for hunting exoplanets? Any new techniques on the near horizon?
For hunting for exoplanets, he says. The transits and the radial velocities, those are by far the best game in town. People have thought a little bit about microlensing, for example.
Yep.
That is what happens when you have an object lensing light from a background star, and so you can measure the mass of the planet that way. I think people have pulsar timing is actually the first exoplanet discovery, I think, in 1992. It was looking at the subtle changes in the timing of a pulsar pulse. This is a radio pulse that we get from these rapidly spinning neutron stars, and they measured a slight disturbance in the pulsar timing, and so they found planets around a pulsar. It was really amazing.
Yeah, we did hang out on that once a while about that. Was pretty freaky. That's a pretty freaky way of finding it.
Very clever. So people come up with these very clever ideas of looking for exoplanets. I'm sure there's a few others, but I'm afraid I'm
well, those are the ones I can think of too. I was going to say microlensing was the most was a popular one as well. So there's also direct imaging, but that requires equipment we don't have right now, that star shades or coronagraphs.
Well, we've managed to do some direct imaging, but it's a small number of planets. You really you want it to be very close. The star should be very close to our solar system, because you can imagine the closer the star is, the wider the sky separation of the planet. You also want this planet to be very far away. We're talking 10 astronomical units or more, maybe even farther than that, something like as far away as Saturn or Uranus is from the star. And then all these systems tend to be pretty young, which means that the planet is actually shining from its own formation heat. We're seeing it in the infrared, and it's shining by its own light. It's not visible by reflected light. So you put all of those criteria together, and you can see that, even though we've been doing direct imaging for, over a decade now, we still have maybe 10 or 15 planets that have been directly imaged. It's very challenging work. So hopefully going forward, we'll have something like you say, star shades, or we'll be able to shrink what they call the inner working angle, how close we can get to the star. And be able to see the planet. But it's very challenging right now.
Okay. Yeah, I just want to welcome Hiptacular Raptor. Boy, on Twitch, only on Twitch do you see these kinds of Twitter handles. Anyway, welcome. I want to thank you for commenting on Twitch, because I worry about Twitch. Twitch is like this. I got 3 people there. I want to thank you for watching, guys. It's really nice. Ask questions. I'm watching. I'm looking at what you're doing. So back on YouTube. Galaxio wants to know, are there any astrophysical signs so that they know the star, this is Kepler-1625, the star, is almost becoming a red giant? You said it was moving up the...
Right. That, again, is, and that's not terribly in my realm of expertise, but this is has to do with spectroscopy, looking at the lines, the atomic or molecular emission lines, usually atomic in the case of a star. Looking at emission and absorption lines, they analyze the spectrum of the star. From there, they can measure the surface gravity of the star. So we know how far away it is. We know how bright it is. We know what color it is, basically. And we can measure the surface gravity of this star. So all of these lines of evidence put together, you can infer the size of the star.
Okay, and habitable zone. Are we in it here? It doesn't really matter, I guess, since this is a gas giant orbiting, or it's a gas giant with a Neptune gas giant orbiting orbiting around. I guess it doesn't matter, but are we in the habitable zone here or not?
Yeah, it sort of depends on how you define that, I guess.
Well, as what everybody else, liquid water, so, if it had it, would be liquid, or water, if it had it, would be liquid.
Yeah, that's interestingly enough, a sort of more controversial definition in terms of where
what everybody uses, though.
Zones. Yeah. But the equilibrium temperature that we might that we derive for this planet is something like 350 Kelvin. That's pretty warm. You look at the Earth, for example, the equilibrium temperature is, I think, below the freezing level, and what keeps our liquid water in place is the greenhouse effect. A little bit of the greenhouse effect is a good thing. It keeps us warm. It keeps water liquid on the Earth. So this one is going to be a little hotter than that. What's interesting is that because this star looks like it's climbing the giant branch, this planet is getting warmer than it once was, and so there would have been a time probably that this planet was a little more temperate. This planet and this moon system were a little more temperate, potentially in the habit.
Okay, help me with equilibrium temperature again. I'm sick of this liquid water crap. What do you mean by an equilibrium temperature?
This is just the temperature that you would measure based on its proximity to the star, having not taking into account at all the greenhouse effect that you might have.
Oh, so it's the temperature it would be if you're sitting at that distance from a star, but without an atmosphere or any greenhouse effect,
and basically perfectly absorbing this incident radiation rather than
Okay, so all other factors.
The planet is very white; it's reflecting away a lot of this light, and so it would be cooler. So we're not taking into account an albedo.
Understood. And you said this one was how much again? 300?
About 350 Kelvin.
Okay, so that's pretty warm. So I have to do the conversions, but that's pretty hot. Okay, Hans Milling wants to know: we have binary stars. Couldn't binary planets exist too? Well, that's kind of what we got here, isn't it?
So this question has come up a lot, whether this is a planet and a moon or a binary system. I think it's a matter of semantics to some degree. What we're really talking about is where the center of mass between these two objects is. You look at Pluto and Pluto's largest, what I would call a moon, Charon, right? Pluto and Charon actually orbit a common center of mass that lies between the two objects. So some people would call that a planet and a moon. Other people would call that a binary planet. As I said before, our solutions for the masses of these objects is not terribly well constrained, but our best estimates place this center of mass within the planet. And so that, I think, is comfortably, you can comfortably call that a planet and a moon. Obviously, this object is much larger in size than any other moon has. That, like I said, people really haven't anticipated a moon this size, but the mass ratio is only about 1.5%, and that's basically comparable to the Earth and our moon. It's a little closer, but that mass ratio is about the same. So, even though this moon is so large, I'd call it a moon still.
So if to keep that mass ratio the same, if the Jupiter had a moon that was roughly the same proportionate as our moon is to us, it would be Neptune. More or less, yeah. And we're talking, again, we're talking about a planet that's a little more massive than Jupiter, but not terribly more massive, at least as far as we can tell. So Alex Reinders, yes. When is a moon, or a pair of planets? I think this mass ratio kind of does it, doesn't it? I mean, if two planets are more or less the same, if that mass ratio is, 1-to-1, then you kind of have a pair of planets, don't you?
Right, yeah, and it has to do with the separation too, right? You can imagine you get farther apart, then that center of mass between the objects starts to kind of drift outward a little more, and so eventually it might be sitting between the two objects. But as far as our modeling says, this center of mass should be inside the planet.
Okay, Raj Luthra, what am I going to do with you, man? Here's this question. Is it possible that this exomoon may have a moon or moons orbiting it? Raj, you're the one that always wants to know about exomoons. We talk about exoplanets. What about exomoons? We talk about exomoons. What about moons of exomoons? You're just not satisfied, are you, Raj? Okay. All right. So is that even possible? Can we have a planet in orbit around a star with a moon in orbit around a planet with another moon? I don't even know. orbiting that
as
moon.
a matter of fact, the question isn't so wild as it might seem. It just made news in the last. It was going around on Twitter. A paper came out. Someone wrote a paper asking about these things called what they call submoons, but in other circles it was promptly called a moon, and Twitter is going nuts.
I know that's what he's asking about. Yeah,
for the moons. So yeah, it escalated quickly. This paper was a very short paper that came out. It's only about 3 pages long, where they analyzed the stability of a moon around the moon, and they said, if the moon, I know we're not talking about the moon, we're talking about the regular moon. If this moon is large enough, meaning massive enough in this case, if it's far enough from the planet, and the moon, or I think most of us prefer submoon is probably a better term for these things. If that submoon is small enough, then you could potentially have something like that stable for a long period of time. The question naturally arises, how might you form something like this? And this paper didn't really treat that question.
Well, the answer is it's moons all the way down. That's the answer. So
exactly right.
I mean, here's what bugs me about this, though, Alex, and I'm going to get your opinion on this. I saw that story, too, and I do a weekly, or whenever I can do it, a video series called Space Fan News, where I try to pick up something that interests me, that I think is interesting to someone else, and I'll report on it. And one thing, I'm starting to see a trend. You said this paper was very short. It also wasn't peer-reviewed yet. And one of the things I'm noticing that a lot of science news websites are doing, and I want to know if you notice this too, is that they are looking at AstroPH, or AXRV, or whatever you want to call that. I call it AstroPH, which is this preprint on that Cornell runs, where people can post on this whatever they want, really, but generally astronomers only do that after they've been accepted into a peer-reviewed journal. They want to get their preprint out there so people can comment on it and get the word out, and also to prevent being scooped. But I'm noticing a disturbing trend on the science communication side where people are starting to read AstroPH and look at the titles of papers that are interesting, and they'll report on them before they're even peer-reviewed. Have you noticed this?
Yes. Well, it's definitely a thing. So in terms of whether or not you should put something up on the archive or AstroPH before or after peer review, there's really sort of two opinions about this. I have tended to think that we should wait until peer review before we put it out there, because so many people access this paper, and so there's an expectation that anything on the archive or AstroPH has already been peer-reviewed. Other people come down differently and say that this is really the best peer review that you could possibly imagine. Rather than having a single referee assigned to you, you're getting more eyes on your paper, and therefore more people are going to be reading it, commenting on it, and giving you feedback.
Except that anybody can post on it. And a lot of stuff can be viewed. You can view AstroPH as an authority, but it itself isn't peer reviewed. And someone can pick a paper off of that and think it's real science, report on it as if it is.
Sure.
And it can be total crap. I've seen it.
In order to post originally to this thing, you have to be sort of verified that you have someone vouching for you, essentially. But that doesn't stop a number of sort of kooky papers getting posted there every once in a while, and we usually get a good chuckle. Hopefully, the science journalists are seeing which ones are a little more legitimate.
I hope so.
This is relevant, though, because when our initial finding, our Exomoon candidate made news about a year ago, last August, we first got attention for this thing. Because in that case, we hadn't even posted anything to the archive. It came out that we were going to perform this observation with Hubble. Once you have a proposal to Hubble accepted, they publish all of the titles and all of the abstracts for those proposals. And so it was spotted that we were going to make this observation, and they were going to write an article about it. And we asked them not to. The publication, I'll leave nameless, but we asked them not to put this out because it wasn't ready for everyone to get excited about. This was a candidate, and it wasn't... It wasn't ready to, we knew everybody would get excited about potentially the first Exomoon, so this was premature. They decided, we're going to publish it anyway. We don't just report on peer-reviewed results. We report on, all manners of comings and goings with respect to the science. So at that point, we really got ahead of we had to make a decision in very short order. What should we do? And we decided to put that paper out on the archive before peer review. So
but it had been accepted, right?
At that point, it had not been accepted. We were about to
so
submit.
You got a little anxious, huh?
Our thought process was we have to get out in front of this and show the community what we're seeing, what we're claiming, and what we're not claiming, because we didn't want it treated just in the science journalism. All kinds of sensationalism that's possible. We don't have control over what people are going to write, and so we put it out in the archive for the purpose of being transparent with the community. But ordinarily, I tend to be of the feeling that we should wait till peer review before putting on the archive, because there's that expectation that it is.
I applaud you for that, and I understand the need to get it out there and get in front of it before others do, or to make sure the proper word gets put out. And science communicators and space news websites, I get that they need to get something interesting and be the first to do it, but I worry that there's not being any careful look. I mean, it does depend on the reporter doing it and looking at AstroPH. Does that person know that this is probably going to be peer reviewed, or is it just somebody who's putting some fringe stuff out there? And while you're right, there isn't that much fringe stuff there. There is some. I've seen it, and so I worry about, in the rush to be first to publish a story, people have learned about AstroPH and now they want to use it to get a scoop on things. So, but one more, because this interests me, I want to ask about the peer review process in your case on this research. When you posted on AstroPH, you said you had the paper written. Were you confident that you would get into a peer review journal? And how do you think about that? How does that work when you write a body of research like you guys have done here with this Exomoon? What do you then do with, do you already have a journal in mind that you want to give it to? And do you have a reasonable expectation that they're going to accept it after peer review? How does that work? Really?
Certainly, yeah. So I'll be clear about what happened in August 2017. First, we had been writing this whole other paper, an analysis of almost 300 planets, trying to look at the population of exomoons. Actually, I won't go into all the gory details about that. And it was and that paper was basically ready to be submitted to a journal, but at the sort of the last minute, because we had to get out in front of this, we dropped in a whole new section about our candidate 1625b, and that's what we put up on the archive. I think we had confidence that our analysis was very thorough. We really knew what we were doing, and as I mentioned before, David Kipping is not just a pioneer in exomoons, but really he knows what he's doing here. So that's not an expectation that there aren't problems with your paper, because there's always going to be things. This is part of the process. The referee reads your paper and says, okay, well, this looks pretty good, but this is a problem, or you can't make that assumption, or this is wrong. Look at those numbers, explain this to us better. There's a lot of back and forth, and you will get pages and pages and pages of notes from the referee sometimes telling you you've got to make all of these changes before it's accepted. But in general, we have a sense that this paper will be worthwhile once it's passed this peer review process.
Yeah, that's different than if there's no intention whatsoever of a journal ever taking it, but you post it there in the hope that people will read it. And while I agree that's not a huge problem on AstroPH, it is something I have seen from time to time. Jeffrey Scott has a good question on Facebook. Let me ask you this one. Will the new class of large observatories like the 30-meter telescope, the extremely large telescope, the stupendously amazing super ultra mega telescope that are being built around the world, will they be able to help you in this research, and can you directly observe exoplanets with them? Do you know?
I don't know terribly much about the direct imaging. I think they will be great for direct imaging, but that's a little out of my area of expertise. These mirrors, because they are so large, we can expect to get incredible photometric precision. Each data point that we take, every measurement that we make of the brightness of the star will have some uncertainty, right? There's all kinds of things that, just noise in the data is inevitable. But the noise will be very, very small for these extremely large mirrors, and so that's going to be fantastic. We'll be able to see smaller and smaller signals. Remember that the expectation, even though we found such a large moon in this case, or we think we found a large moon in this case, moons are expected to be about the size of the Earth or smaller, right? So these dips are very, very small and are almost always, at least in the Kepler data, going to be lost in the noise. So we might, with these giant mirrors, we're going to do much better, and we could really possibly see these dips. The bigger issue is that, we still have to, we think, look at much colder planets, and so those transit durations are very long. Yeah. That complicates, as I said
still
before,
got that Earth rotation problem, don't you?
Observation from the ground, yeah. So still, all kinds of new challenges going after these things.
All right, cool. All right, and Jeffrey, let me just point out, you're going to want to watch the Telescope Talk professional version of our Hangout not this coming Tuesday, but the following Tuesday, which I think is the 23rd. I've got the director of the TMT on to talk about the what's going on with the 30-meter telescope. So you want to check that out. That's a Tuesday on Telescope Talk. Tuesday Telescope Talk. I love the alliteration of that. In a couple weeks. So you want to check that out. Okay. I think we are done. Let me just do a real quick scan on some of the questions here. I'm looking for the big question mark. Alex Despland wants to know real quick, and then we got to go because we're out of time. How far away is Kepler, and where is it in the sky? It is leading the Earth in its orbit as around the sun. So it's never in one spot in the sky. I forget if it's 1 million miles ahead of us or how far away it is. But as the Earth goes around the sun, Kepler is ahead in that same orbit doing its observation. So it's following along on Earth's orbit around the sun. And for a long time, for the first 5 years, it was only looking at the constellation Cygnus the entire time. But since then, the reaction wheels have failed, and problems have happened on the spacecraft such that it could no longer look at one spot. So now they were using solar pressure to hold it steady while they looked at all of the stars along the ecliptic plane. That's the path that the sun follows, or the Earth follows around the sun. And so that now it was doing a lot more science as K2. They renamed it K2, but now it's back in safe mode. It's like super out of fuel. It's running on fumes right now, and they don't know how much longer it's going to last, but they're in campaign 19, I believe, and they might get data, they might not. It's one of those things where they didn't put a gas gauge on Kepler, so they don't know exactly how much it's got, but it isn't much. And poor old Hubble's having trouble too. I hope you get Hubble time. I really do, Alex, because it looks like it's also going to be hobbling on one gyro for a while. So hopefully,
yeah, we'll have to see about that. I'm not as necessarily worried about it. I think that's like so many things, there's a lot of sensationalism, maybe, or people freaking out on Twitter. News gets out and it gets blown out of proportion. I think. If we're awarded that time, we should be able to get some science out of, some good science out of Hubble. But we might be dealing with new difficulties that we didn't have.
Yeah, that's one reason I wanted to pick. When Carol comes back, I'm going to pick her brain on this on the next Hangout because she's the Hubble project scientist there. So I'm going to ask her about this business. Nobody seems worried. Everybody says, hey, it's going to point just fine on one gyro. If it has to, it's not great. It's not ideal, but it can, and it's done it before. And we'll keep another one in spare if they can't get this third one that went wonky to work again. And
right. So, if you look at the K2 data, this K2 was as you were mentioning, the second life of the Kepler telescope. Mm-hmm. There was a lot of drifting going on in this data, so it was not nearly as stable. I mean, it was really still remarkable, but it was not at all as stable as the original Kepler mission. And folks came up with really clever ways of dealing with that data. So we'll make Hubble work one way or another, as long as it's still pointing.
Okay. All right, Alex. Well, listen, I want to thank you so much for taking time out to be on our Hangout. I hope if you do get more Hubble time, or if you do get some kind of confirmation, you'll consider coming back and letting us know what's going on and whether this thing has been confirmed or not.
I'd be happy to. Thanks so much for having me.
Thank you, Alex, and best of luck on future observations. Okay, folks. Well, that is it for this Astro Coffee Hangout. Next Thursday is Future in Space with Harley Thronson, and I don't have the topic yet for it. However, Tuesday, we got telescope talk every Tuesday at 3 o'clock. Now, as you know, I try to switch back and forth between pro and amateur version. But we've got 2 pro versions in a row because of scheduling issues on the Astronomers. Next week, I'm talking with Hector Socas Navarro from the Institute of Astronomy in the Canary Islands in La Palma, and he's going to talk about Clark exobelts, which is a technosignature that people look for the satellites around exoplanets. So you're going to want to watch that. He's doing that from a ground-based observatory in the Canary Islands. And then the following week, like I said before, we've got the 30-meter telescope project manager on to talk about the status of that mission. It's a 30-meter telescope, big, huge, massive, being built now, or at least it's going to be starting, I think, next year. So tune in next Tuesday and then the following Tuesday for that. So that is what we've got coming up. I have a big announcement coming up probably next week on some sponsorship stuff, which I'm excited about. So I'll let you guys know about that when it happens. And on behalf of my guest, Alec Teachey, I want to thank you all so much for watching. And as always, keep looking up.